This question is about reflection and total internal reflection. So it says that light reflects from a plane mirror, and then it says use words from the box to complete the sentence below. We've got less than, equal to, and greater than. When light reflects from the surface of a plane mirror, the angle of incidence is something to the angle of reflection. We know, because of the law of reflection, that the angle of incidence is always equal to the angle of reflection, so the answer must be equal to. The second part of the question shows two rays of light coming from an object. It asks you to continue the two rays and add further lines to the diagram to show how an image is formed by a plane mirror. Now, whenever you get this sort of question, the first thing you have to do is draw the normal line. Now, the normal line is a line that goes at 90 degrees to the surface of the mirror or reflective surface. And you know, in this case, the image is going to lie somewhere along this normal line. But we need to use some more construction lines to find out where exactly that image is going to be. So the first thing we do is we extend this line up to the mirror. We're going to have to draw on another normal so that we can carefully reflect the line back, making sure that our angle of incidence is equal to our angle of reflection. Then we're going to do the same again to the second line. So again, nice straight line, and then carefully draw in the normal, and then once again reflect that line so that the angle of incidence is equal to the angle of reflection. And then the final step is to extend these lines back, again with a nice straight line. And what you'll notice is that these lines always intersect at that point on the normal. And so this point right here is where our image is going to be formed. Now, the next part of the question asks us how we know that the virtual image has been formed from our diagram. Now, a virtual image is an image that is not really where it appears to be. If we were to look behind this mirror, we wouldn't see this image. It's just that when we're standing in front of the mirror, it appears that there is an image here opposite the object. And one of the things that always happens when we have a virtual image is that we have diverging lines. So if we look here, we can see that the lines are much closer together than we can see here. So we say that the lines are diverging. So we can just write that the lines reflected off the mirror are diverging. Part B says light can also reflect along optical fibres by total internal reflection. And then it asks us to complete the diagram to show the path of the ray of light as it enters and passes through the optical fibre. Now, total internal reflection is when all of the light is reflected back inside of the medium, as opposed to some of it being transmitted and refracted out into the outside. And so the first thing we've got to do is we've got to extend this line on until it hits this boundary just here. Now, it's totally internally reflected, so none of the light is going to escape out of here. It's all going to be reflected back inside. Now, you'd be sensible to draw a normal here so that you get a decent reflection at that point where, again, the angle of incidence is equal to the angle of reflection. Now, the examiner's not going to get out a protractor at this point and measure to make sure that your lines are exactly, to a degree or even a couple of degrees exactly the same, they're going to want to see that there is approximately a drawing that is obeying the law of reflection as it goes through here. And if I was to get out a protractor and measure each of these angles of incidence, each of these angles of reflection, then, I think the most they're going to be out is perhaps a couple of degrees, and that's absolutely fine. The next part of the question asks you to state 2 conditions that are required for total internal reflection to happen. Now, the first one is really what defines total internal reflection, and it's that the angle of incidence has to be greater than the critical angle. And so the image I always think of here is that, let's say we had a semicircular glass block, and I'm going to draw in a normal here, and let's say that we shone a ray of light through here. If this angle here was smaller than the critical angle, then we're going to get refraction happen. So it's going to come out here like this, where we've got a larger angle of refraction because it's gone into a less optically dense area around here. If we shone another ray of light, and this angle here, again, could be less than the critical angle, then again, we'd have refraction. If we shone another one at a greater angle, and let's say that this time, this angle here is exactly the critical angle, then the ray of light is refracted right along the boundary of the material. And even if you went a fraction of a degree with a larger angle of incidence, then you would get that total internal reflection. So that's what that first point is about. Now, the second point is that it has to be moving from an area that is more optically dense into an area that's less optically dense. So for example, here and here, we've got glass, and then we've got air and air around. And glass is more optically dense than air, and therefore total internal reflection can happen. So for the second point, so the medium must be more optically dense than the outside, or you could say it has a higher refractive index. And the last part of this question says that telephone signals can be sent along optical fibres using light. In earlier systems, signals were sent using electric currents in copper wires, and it asks us to suggest one advantage of sending signals using optical fibres. Now, if we sent a signal using electric currents, then that's going to cause the copper wires to heat up. And as the copper wires heat up, the atoms of copper start to vibrate more, and then this causes resistance to increase, and it's harder for the current to pass through. And so, if we're using those currents as a signal, that's going to introduce a lot of noise into the signal, and so when we pick up the signal at the other end, it's not going to be as clear. Whereas with optical fibres, you don't get that heating effect to the same extent, and so the noise is much, much smaller. So we could say that it has a smaller signal to noise ratio, or a larger signal to noise ratio. So we can just say that it's less prone to picking up noise. Now, it's really important that you don't say it doesn't pick up noise, because that's just not true. It will pick up noise, but just not to the same extent.